everybody. BW. Awesome. Thank you. So very excited to have you all here today. Beautiful day. Finally, the heat's kind of broken a little bit. It's nice outside, nice to walk around. You don't come in drenched, which is just fantastic. But we were very, very fortunate today with our speaker, right? So over the last several decades, humanity has developed the capability to manipulate molecules and atoms at sort of the nanoscale level. And this kind of technology has the ability to have massive changes in new materials in areas like energy and healthcare, and really change the way we solve some of our nation's hardest problems. Our speaker today is Professor Vladimir Bulovic from MIT's Electrical Engineering Department. Professor Bulovic was the founding director of MIT Nano, which is really the center across all of campus for nanotechnology research. It supports over 1,500 students across campus, over collaborations with over 100 plus companies. Professor Bulovic also has authored over 300 peer-reviewed papers. He has 120 plus patents, and he is really one of the nation's leading thinkers in this really important new developing area. So with that, I'd like to introduce Professor Bulovic to take it over.
Thank you. Thank you for having me. Is this on? Yes, good, excellent. It's an absolute joy to be in front of you. I'll start by saying that give it 10 years from now, and your job will be to run this world. Yeah. Yeah, no, don't forget that. Everything that you're learning now is really just a smidgen of what you will be developing as the world keeps turning and solutions, new and new solutions need to be provided. Everything I'll tell you today, in a year from now, will sound like old news because there'll be so much more that we will develop. And our job collectively, and by saying our, I mean mine and your together, is to kind of figure out what is it that the world truly can use to make it an even better place than it is today. How do we build that better world is really a mission. I get particularly tickled by the mere fact that down on the nanoscale, many of the solutions lie. As a matter of fact, nanoscale has been actually the answer to many of the solutions we already have brought forward. We just often don't think of it that way. The nanoscale often is seen as a dimension that maybe is unfathomably small or not easy to reach or possibly not necessarily something that I should worry about now, but when I become a PhD student one day and get my doctorate or a postdoc or a professor, that's when I should start thinking of nanoscale, and that's a mistake. Nanoscale is for right now, for you to think about. I would ask you this. So this morning, as you were preparing for coming to MIT, and maybe you had a glass of orange juice in front of you. You smelled that cup of orange juice and something reached your nose. Something that made you know that inside that cup, there's orange juice. What reached your nose? Any thoughts? Yeah. The scent. Yeah, absolutely, the scent. What's the scent? Say again? The particle that left the orange juice and reached your nose? Yeah. Please.
A small evaporated particle of the orange juice from the surface of the orange juice.
A small particle that left the orange juice and traveled through the air, reaching your nose. All right, how small is it? Any thoughts? How many nanometers is it? I gave you a hint there. And the answer, whenever I ask a question like that, the answer is always a very simple answer. Yes, any thoughts? 1 nanometer, that's correct. Anything you ever smelled, any scent that you have experienced happens to be 1 nanometer in size. Now, why is that? Well, because it turns out if you have a small object, a nanometer size object, the only reason why it's actually attached to the rest of the orange juice is because there is a so-called van der Waals force, polarization-induced polarization kind of force, where you have a plus and a minus in the molecule, and that causes the other molecules to change their polarity a little bit, and a plus attracts the minus and keeps that molecule from leaving the cup of orange juice. Except once in a blue moon, because everything in a cup of orange juice is wiggling, right? Because it's not at 0 Kelvin, it's at higher temperature. As it's wiggling, there is a finite chance that two molecules underneath the one that I'm going to eject out are wiggling, and they wiggle just in the same way, giving the energy to the one on the top to be propelled out. That's, by the way, why if you leave a cup of water next to your bedstand, a fraction of the cup of water is missing by the time the morning comes. And that's because those molecules wiggle over the night, and the one on the surface once in a while get ejected and leave. The smaller the object, the fewer attachment points it has, the fewer places it can induce the polarization, the van der Waals bond that keeps it in the cup. How small can we get things get? Well, about a nanometer is about 10 to 20 atoms that get linked together to make the molecule. So every scent you ever sensed is 1 nanometer in size. Wait, whoa. Does that imply that my nose is filled with nanoscale detectors? Yeah. You guys are designed to smell nanoscale. Every time you do smell a smell, you are smelling nanoscale. You are the nanoscale detectors. Very precise nanoscale detectors that can distinguish actually even sub-nanometer feature. The molecule of orange and lemon, the scents of orange and lemon, those molecules happen to be exactly the same molecule, except one is concave and the other one is convex, so-called cis or trans molecules in chemical language. And as a result, it's that nanoscale, sub-nanoscale misshapenness of the molecule that you're detecting if you can differentiate between a scent of orange and a scent of lemon. Nanoscale is all around us, but often we don't have an easy way of telling a story about it. I told you one about the way we smell things. It turns out every sense in your body uses nanoscale to make its determination of what the world around you is. I love ice cream, and once in a while my kids leave the ice cream on the counter and it melts. And then I try to save it by putting it back in a freezer. And next thing I know, it's frozen again, and I taste that second frozen ice cream, second time frozen ice cream. Does it taste very good? No, yeah, thank you. Those of you who've had a similarly disappointing experience, no, it doesn't taste very good. But the challenge here to me is why not? I mean, it's exactly made of the same chemicals that were there before it melted and refroze. So what is it about this new ice cream that doesn't meet my sense of taste delights? Yeah.
Is it because that it takes longer time for the crystals to form, and then it affects the texture because there are larger crystals, it gives the texture much as when it was formed quickly with the very quick.
I'll repeat that just because online people might not have heard you. The suggestion was that maybe it is the fact that during the melting process, you can give now enough energy to the liquid of puddle of ice cream to make maybe larger crystals of sugar, or maybe vanilla crystallizes in some other way. And as a result, these now larger and differentiated crystals, when they interact with your tongue, they don't melt quite as easily. They don't stimulate the sensors in your tongue quite the same way. It's also, yes, other thoughts?
It's flash frozen, the crystals forming insanely fast. So if you ever had those very, very sweet.
The liquid nitrogen ice cream also tastes really good, was also suggested. Yes, another thing about ice cream. Yes.
I think it might be because of, like, maybe there is less air in it, so it's not as fluffy and the texture is worse.
You don't like it because liquid nitrogen ice cream because it's not as fluffy, because it doesn't have as much air in it. Just like refrozen ice cream doesn't have air in it as well. I'm with you. It's the churning process of the ice cream that introduces little voids inside the ice cream. But why would a void really matter for my taste? Void is an absence of taste. It's kind of like asking a question, if I'm going to paint a picture and I'm only going to use white and black colors on a gray background. Well, if it's only whites and blacks, those are very distinct, very sharp standing colors that I can easily pick with my eye. If instead, though, I blend it and I have only gray on gray, the contrast diminishes and the impact of the contrast diminishes. Voids of taste give me a chance to experience the taste right next to it a little bit more poignantly, a little bit more strongly. And so incorporating the voids actually is a way to accentuate the rest of the tastes that are present inside the ice cream, and as well, make sure that the crystals are not too big, because otherwise you can't easily dissolve them and hence sense that taste as well. Everything we just discussed is a nanoscale phenomenon. Every one of those tastes that you're looking for, the scent or the taste of vanilla, is a nanoscale object that your tongue is experiencing. So your sense of smell depends on nanoscale, your sense of taste depends on nanoscale. You think the other senses depend on nanoscale as well? Yes. Everything you ever experienced is a nanoscale experience. You just don't think of it that way. And so my goal, and we can go through many different ways of telling the stories, nanoscale is everywhere. There is no discipline as nanoscience and nanotechnology that is just standing on its own. Nanoscience and nanotechnology touches every discipline we know. Anything to do with the physical objects, anything to do with the making of things as we know them, is it in electronics or in chemistry or in biology, happens to be a nanoscale phenomenon. The thing that happened over the last 2 decades, over your lifetime, is prior to you guys, we did not have the tools to see the nanoscale. We could infer it. We could maybe see the glimpses of it. But it's the tools of the last decade that truly enable us to come up with transformational rethinking of what nanoscale can give us. We are entering, as I think of it, as the dawn of the nano age. There is a tremendous amount of new discoveries that will come because a picture is not worth 1,000 words, it's worth 1,000,000 words, as one of the recent Nobel Prize winners said. The discovery of the opportunity is really in understanding how the world is put together and then restructuring it to make that next set of grand ideas. So, if anyone ever asked you how big is nanoscale, what would you guys say? I'm just trying to make sure we have additional hands. Yeah, please. Around 20 atoms, that's a good one to put together. The distance between the 2 atoms typically is on the scale of 0.15 nanometers. And so make a blob, because it's 3-dimensional, and you're going to get yourself to about 20 atoms. Huh. Any other way? I mean, because I don't know how small the atom is. Any other way to describe nanoscale? Yeah. Tell me. Oh, like this? I have maybe a slide that does exactly that. Let me just make sure I can actually forward. Like this. The hair is right there in the middle. So if you compare a hair to a 1 nanometer wide carbon nanotube, the ratio of the two is about 1 to 100,000. The width of a human hair to a distance across this room is also 1 to 100,000. So a hair is to the width of this room as a nanometer is to the width of the hair. That does really help. Other thoughts? Yeah.
The wavelength of visible light is also at a nanoscale.
The wavelength of visible light is also nanoscale. How small do you think it is?
I think it's like in the hundreds, like right is like 600.
Yeah. So 600 nanometers is roughly red light. 500 nanometers, a little more, 520 is green light. And 450 nanometers is blue light. So wavelengths of light in air Because when you change index of refraction, you shrink the wavelengths by the index of refraction accordingly. But in air, it's a few hundred nanometers and you get yourself visible light. If you get yourself to 300 nanometers, that's too short. It's amazing. Nanoscale seems to be all around us. We can actually control that nanoscale extremely precisely. And it turns out that if you take a piece of gold and make it very, very small by taking a chunk of gold and then cutting it in half and then cutting it again in half and keep cutting it until you get it very, very small, you can get yourself nanoparticles of gold. Now, no one ever does what I just described. No one ever actually takes a chunk of gold and slices it down. What you do is you start from atoms of gold and you coalesce them in a liquid state to form little colloidal nanoparticles that grow bigger and bigger and bigger. And you can choose the size of the particle you would like to make. A small one, a little bit bigger, or a little bit bigger. Do it similarly for silver, and gold and silver will look like this. These are nanoparticles of gold and silver swimming in a liquid of some sorts. Water, benzene, ethanol, doesn't matter. Yes? I'm sorry, I couldn't hear that. Oh, I was about to say that the oranges and the yellows and the reds, those are gold. And the blues and the greens are the silver nanoparticles. Yeah?
Why are they all not the same color? Like the golds, why are they different colors?
Because the particles are of different size. You know, you said something really cool when you said that the wavelength of light, it happens to be 100 nanometers in size. That's because we are okay treating light as a wave. You also heard of light being a photon, right? So light is both a wave and a particle. How about the electrons? Are they waves or particles? What? They're both? Electrons are waves? They're, everything's a wave and a particle. You're absolutely right. Everything is a wave and a particle. And the fact that you guys know that is an awesome step up for humanity. The fact that you as high schoolers are looking at the world around you and not thinking it only as a wave or a particle, but recognizing that it's both. That is the key to what we now call casually quantum mechanics. And it happens to be actually the way that the world is truly described. It's not difficult. There's nothing, odd about it, except it's not something we experience easily. We are okay saying that you can interfere light and form little interference fringes. It turns out you can similarly interfere electrons if you shoot them, just like you can shoot light through two slits and get a pattern of fringes. If you have an electron and it has an option of going through two slits, it's going to form a fringe pattern of where the electron lands on the landing screen on the other side, similarly, because he has a wavelength just like light does. Because of it, if I give you a box in which the electron needs to sit, if the box is very small, I can only fit certain number of wavelengths of electron as I go around the circumference of that chunk of matter. That's the only place the electron can be, in that chunk of matter. It can't sit outside it if it's going to be in that chunk of matter. And then you can fit electrons of different energy, have different wavelengths, just like photons of different energy. So electrons can have this energy, or this energy, or this energy, depending on how big the nanoparticle is. Notice I didn't give you the energies in between. I only said certain multiples of the wavelength can fit around the circumference, which means there's discrete energy levels. Change the size of particle and I just change the ground state from the excited state distance. And hence, the nanoparticle color will change by simply changing its size from 10 nanometers to 15 nanometers and any size in between. This is a well-known fact that goes back to the Middle Ages. It does. The nanotechnologists of the Middle Ages made stained glass windows using this fact. They had all the calculations down. They wrote down the Schrodinger equation and figured it out. They didn't. They actually followed grandma's recipe that said, go to that side of the mountain, take a rock, make molten glass, toss the rock in, add a little bit horse's hair, cow's milk, do the right dance, make sure it's full moon, and you're going to get yourself the right color stained glass window, right? Today, though, we have the tools to peer into that stained glass, and what we find is inside the stained glass, there are little nanoparticles of silver or gold or other metals. And those nanoparticles have a particular energy level structures that reflect particular colors of light as it's incident upon it. Change the size of a particle, you'll change the color of your stained glass window. Stained glass window lives a long, long time, doesn't age because all it is a glass that doesn't age, it's already oxidized, and metal that's encapsulated inside the glass, and hence will be protected by the glass as it ages. Now, this is a simple nanotechnology discovery. In the 21st century, though, we can use it to make a diagnostic for medicine. I told you that the size of the particle changes as it gets a little bit bigger. So what if I can take that nanoparticle and put on it molecules that happen to have fractions of a DNA strand of COVID or Zika virus or West Nile virus? If Zika or West Nile happens to be present and can attach itself to the coating on those nanoparticles, the particle will effectively be a little bit bigger. It has the particle, has the coating, and now has the little chunks of Zika or West Nile or whatever else attached to it. Particle that's a little bit bigger has a different color. So if you're in the lab of Professor Lee Gerke here in biology, you can take those silver nanoparticles, add to them ligands, molecules, that happen to have the fractions of the DNA strand that correspond to a particular virus. And all you do is you paint these nanoparticles on a piece of paper, you put a drop of blood on that piece of paper. Paper is a microcapillary medium, it's porous. And just like if you put a drop of coffee or tea on that paper, it would spread. Same thing, put a drop of blood on it, the paper will carry the whatever is in your blood to the particles. If there happens to be fractions of the DNA strands of Zika or West Nile or whatever other disease you're looking for, and it reaches the particles and the particles change color, you have that infection in you. From perspective of diagnostics, this is a much, much cheaper diagnostic than any other that we're aware of. And much more significantly, many of the diseases originate in places that do not necessarily have easy access to medicine. Being able to diagnose in the deep forests of a continent, in a village that is far away from the neighboring cities, being able to diagnose a particular disease would be a significant way of stopping that disease from spreading further. Right now, the way you do it is you would go ahead and take a refrigerator in your back. You would walk a day to the village that's deep in the forest. You would take the blood samples. The reason we have a refrigerator in the back is to collect all those blood samples and carry them back to the city, analyze them in the city, and once you get yourself the results, walk back the following day with the results in order to tell the villagers you are infected and you're not infected. That's several days of work and a lot of carrying of refrigerators on one's back versus carrying a few strips of white paper that happen to have nanoparticles on top of it and just taking a drop of blood, consequently in 20 minutes, getting a diagnostic who is and who isn't infected. A life-changing way of rethinking how to detect medicine, all by using very simple nanoscale technology that has been around since the Middle Ages, just not quite in this format or not quite with this kind of understanding. Yes? It's a very, very long shelf life. You're asking a great question. You don't have to worry about them decaying. The particles, silver will not go anywhere. It will oxidize maybe, but it's probably already oxidized the first time you use it. It's really what you're counting on is the attachment of the ligands. And that attachment can be very, very stable. If you're worried about it, just keep it in a little Ziploc baggie, and that will prevent it from oxidizing or getting moisture damage. So those are nanoparticles that, yeah, please.
So I know that like adding like the DNA of like the bacteria, it's like a very fractional like change. Are our eyes able to like actually like see those changes?
You mean the? Yeah. Well, you know, yes, the answer is yes, you can. Our eyes can pick it out. If your eyes cannot pick it out, your iPhone can, right? Your iPhone is not the greatest spectrometer, but it does have red, green, and blue. And you can have a ratio of red to green or green to blue. Any kind of detection of change in that's you should be able to pick it out. Yeah, it's a great question. All right. Well, so those are nanoparticles that reflect light. There are other kinds of nanoparticles that are designed to absorb light and luminesce back their own colors. These are so-called colloidal nanoparticles, little chunks of matter that happen to, again, be consisting of something that we call a core and something we call a shell. A shell is maybe just one atom or two atoms in thickness. The core itself is anywhere from 2 to 12 nanometers. And if you use cadmium selenide as your core with zinc sulfide as your shell, you will get these colors of luminescent light. Notice the background is black because we are showing you the luminescence of these nanoparticles when illuminated with UV light. UV light gets absorbed, and then they luminesce back their own colors. These particles are very potent, very simple from perspective of how to think of them. And the physics is all about change the size of the particle, make it bigger, and a longer wavelength can fit inside it. So make a bigger particle to make redder ones, have smaller particles, make bluer ones. The way you make them is you put some precursors in a beaker that's hot, you cook the thing, you form a little crystal. If you cook it for a minute, the crystals will stay small. If you cook it for 5 minutes, the crystals will get bigger. If you want to go ahead and make a green color that's right in between, stop cooking after 3.5 minutes. Cool it down, and your particles stay of that size. Then to cap it, you put a little shell on top that finalizes, puts kind of like a nice bubble wrap, you can think of it, around the nanoparticle core. And then if you want to actually dissolve it in some sort of a solvent, put molecules, ligand molecules, capping ligands that make the particle appear like an organic molecule from the outside. You have the fluffy ends that are carbon-based. Whatever is inside, no one sees. And so as a result, this little chunk of matter that has that complexity can now float inside a liquid, like ethanol, benzene, DMSO, or any other solvent you wish. So what do you do with this? You try to figure out how to make a useful technology out of it, like with any nanoscale discovery. Now, I'm just going to ask the question this way. Some of you in this room are thinking about being scientists, I imagine. And some of you are thinking about being engineers, right? Okay, they're fine. That's like doing applied science, right? It's good. Just wondering, how many of you guys are thinking of being scientists? Just raise your hand. Yeah. All right. And how many of you guys think of being engineers? Oh, applied scientists. Okay. Scientists are really cool. I love engineers, being one myself. Did I miss any discipline that you guys want to be? That, like, do you want to be an economist? Yeah, excellent. Did I miss any other discipline? No, okay. Oh, why an economist, if you don't mind me putting you on the spot? Yeah, the business and economics, you're absolutely right. Because I think one thing that often as inventors of new ideas, we often miss is it turns out it takes typically a decade to grow an idea from an invention that all of us have on a board as we're thinking about what next thing to invent. That moment of invention is the beginning of a 10-year journey that follows. And the actual 10-year journey is not an easy one. It requires many of the economic insights in thinking about the techno-economic value of what you invented. You're trying to do the better world. You're trying to make the best world one can through your inventions. Inventions are by far not enough. Of 1,000 great ideas, one becomes useful to the world. Yeah, I know. Of 10 awesome startup companies, 2 will succeed. Not because the other 8 were bad ideas. It's just because techno-economics and understanding of how do you actually incorporate those ideas into the world is a huge challenge. So do appreciate that and don't forget that you do want to also ask yourself, after you get your mastery of science and technology, think about techno-economics a little bit. Because the journey of a quantum dot took about 30 years to go from fantastic science discovery to the first commercial uses of the colloidal quantum dots. Yeah, 30 years. That sounds like forever. It's a long time. It is a long time. And you have to have some amount of faith and belief that it could truly make a difference. And if you are making your very first new inventions, you say, hey, how about this? How about we go ahead and use those colloidal quantum dots? They happen to glow. So let me make a business out of it. I'm going to make a light bulb, right? Oh, but world already has light bulbs. So why do we need light bulbs? Well, world has light bulbs, but not like my light bulbs, okay? Like the world out there, this is, let's imagine 2010, long time ago by many standards. But in 2010, we didn't really have that many LED lights. The primary way we could make a light bulb, certainly in 2005, was to take a filament of tungsten, pass current through it to heat it up. And when it got really, really hot, it was glowing at 3,500 Celsius, right? To make, or 2,700 Celsius, to go ahead, Kelvin, let's say, to go ahead and give me the glow that I was perceiving as an incandescent light bulb. And if I took a bowl of fruit and I placed it under that incandescent light bulb, I would see my bowl of fruit. Now, it turns out that these light bulbs are 10, 15% efficient in converting the energy invested into the light bulb and making light. The rest is heat. That's why if you ever have seen an incandescent light bulb, don't ever try to touch it because you'll burn your fingers, like I've done many times. It'd be better to make a light bulb that is not as hot, doesn't waste as much energy. And that's why we started making LED lights. And in 2009, they look like this. You take a beautiful blue LED, you put a little bit of a phosphor on top of it, and you'll convert some of the blue light into the greenish, yellowish light, maybe even a little bit orange. And you use that as your light bulb. Put your bowl of fruit under that light bulb and your bananas don't look as appetizing anymore because you're missing the red colors. Why are you missing the red colors? Can't you make red phosphors? Well, yeah, you can. You can make red light by using red phosphors that emit in red and infrared because they're very broad emissive spot. They make many colors at once. Issue with that is that I just told you that I would like to not waste any of the energy. And you're telling me put a phosphor, red and infrared emitting phosphor that's going to emit infrared light that my eye cannot pick up. That's not good. That's a waste. So what I can do though, is I can use my little quantum dots. My quantum dots make beautiful pure color. Only one color, a little few colors around a central wavelength. And as a result, use them as phosphors. If you use them together with this, you'll get this now. Just a little layer of my little quantum dots on top of a LED, cool white LED, will make my bowl of fruit appear appetizing again. And I would do it at about 5 times more energy efficiency than an incandescent light bulb would be ever able to provide me. Yes? Why don't I use the right LED? That sounds good. So you're saying make some blue LEDs, make some red LEDs, figure out how to wire them together, figure out how to make sure that one is exactly the same brightness as the other, or at least rationally doesn't change and age over time. You see, I'm trying to complicate the picture. Because wouldn't it be easier just to make a blue LED and paint it with something that will take always 20% of the blue light and make it red, no matter how bright the blue LED is? So techno-economics is the answer, because it is absolutely possible. You know, like those Philips Hue light bulbs are a good example of that. They have independent red, green, and blue LEDs that can be independently controlled. And as a result, you can make any hue you want, but they will not age at the same rate. And they cost a lot more because now you have 3 light bulbs inside of one. They cost 3 times more at least. So cost-wise is the really big deal. And indeed, this made sense to do back in 2010 when the light bulbs, LED light bulbs, costed about $40 a light bulb. And so if I can say it's a $40 light bulb because it's going to last you 10 years, the pitch was, it's going to last you 10 years because incandescents only lasted a month before you need to replace them, right? So these last 10 years, I mean, come on, spend money now. Very few people did, but they did. But in a process, I can tell you my little film on top, 5% of the value of the light bulb should be my film to make money on it. So let me do that. 5% of $40, that's $2 per light bulb. That's a good money. I can make good money on my film. It makes sense for me to learn how to make quantum dots. Until a couple of years pass, and the cost of light bulbs goes down. So today, have you guys ever tried to buy a light bulb in a store? Do you know how much it costs today? $8 for a pack of 8. So it's $1 a light bulb. So 5% of $1 is 5 cents. You can't make a business out of that. That's not something that's worthwhile, despite the fact my light bulbs look way better than anyone else's. I can't sell it because of us, the consumers. Apparently, we don't want to spend $2 on a light bulb. We want $1 on a light bulb. But I can tell you, mine look so much better. They're like, you know, I'll live with a slightly less quality color. These are all big techno-economic challenges. It has nothing to do with science. So what you need to find is a more expensive light bulb. And it turns out there are more expensive light bulbs. Like a little startup company, Q Division, realized that every TV today, every screen today has a light bulb of some sorts. An LED light that sits right on the bottom of the screen. It shines the light throughout the screen and gets emitted forward. Those are like $20, $30 light bulbs. I'm in the right range. So can I go ahead and give you a $20, $30 light bulb that consists of blue LEDs, green quantum dots, and red quantum dots to make perfect blue, perfect red, and perfect green? And that's all you need to trick your eye into seeing any color of the rainbow. That indeed is what became known as, you can buy it today. It's a QLED TV, quantum dot enhanced LED TVs. They use little chunks of matter, quantum dots. They sit on top of an LED light and convert blue into red and green to give you the most vividly looking images on TVs. With $20 or $30 light bulbs, then you can make a business out of. Techno-economics matters a lot, and hopefully I made a point of that, not to emphasize that science is not the absolute key, and engineering of that science is not the absolute key. It is. But the next step of actually making sure that that technology can reach 1 million people is a journey that requires a tremendous amount of techno-economic insights in order to allow you to get to that next stage. So nanoscale is awesome. Indeed, these kinds of quantum dot discoveries, I told you, are technologically very valuable. But beyond technology, scientifically, they gave us a tremendous amount of insights. And indeed, last October, this particular work was recognized by the Nobel Prize. Professor Munji Bawendi, here in chemistry, building right next to us. There's another building right next to it. That's where his office is. He was a recipient of the Nobel Prize in chemistry because of his discovery, and he'll tell you accidental discovery of how to efficiently make reliably colloidal quantum dots that from then on took the world by the storm, and over the 30 years grew into many, many different applications. One of them being the TVs, but there are many more coming. The beautiful thing about the quantum dots is they are perfect instantiation of the nanoscale, very visible, very controllable, and very practical. And of course, Munji is my dear friend, so I took a picture on October 4th. Munji keeps thinking of what other nanoparticles one can make. When you get down to the nanoscale, you realize you can make many different size nanoparticles. These are so-called perovskite nanoparticles compared to the other ones I just showed you. These are particularly unique as they happen to have shown that they can make indistinguishable photons. You might have heard by reading articles here and there that there are such things as entangled photons. Photons that happen to have exactly the same moment in time of being made and happen to know about each other, are connected, are entangled in some way. This particular nanocrystal is particularly efficient at generating entangled photons. And these particular photons are particularly good at things like quantum cryptography or quantum computation, being able to transmit information over long distances instantaneously and so forth. These are a variety of science fiction sounding ideas that happen to be now possibly available through some of these very first discoveries of efficient entangled photon emitters. Notice the publication date on this particular article. It was the late 2023. How soon will this become a technology? Yes, give me the year. What's it? Of course not. Yes, 2033. Thank you, my friends. 53? 53 is also an option. That would be 30 years. I'll give it 10 years. In 10 years, you might find yourself. 30-year journey is indeed a very long journey. A typical invention takes about 10 to 30 years, depending on what you're trying to make. I'm going to be optimistic and say we'll be able to scale it faster. And you know, this is not a technology yet. All it is a little chunk of matter that's giving glimpses of what future technology might look like, because it has a right physical property that scientists recognized, and now engineers need to take on and think about how do you truly make a practical technology out of it. So yes, please.
The current difficulty in the synthesis itself, or in finding applications, they were like, oh, we can definitely just put R&D into this right now. Let's do this.
Yeah. So how would you make a quantum entangled system?
That's a great question.
Yeah. Thank you. I'll stop right there. There's always more to be done in flying to the moon than simply saying, I have all the parts. It is indeed flying to the moon in many of these options. That is why the journey takes 10 years. It's not obvious. It's just a fantastically good start. All right. I'll give you a couple of more nanoscale experiences as you think about how to embrace the nanoscale. Of course, electronics is nanoscale, right? It's all very, very small and very precise and takes a long time to make a right chip to does the right thing. But everything else you experience, I said, is also nanoscale. And those of you who are biologists or bioengineers might not be surprised, but some of the rest of us might be, that to learn that drugs and vitamins are also nanosized. And just as a metric, I drew a picture of a benzene molecule there to give us a scale bar. Benzene is about 1/3 of a nanometer. And here are some medicines you might have seen, like aspirin or ibuprofen. Those are about 3 times bigger, roughly, than benzene. So it's about a nanometer. Vitamins A, B, C, D, they are maybe 1 to 2 nanometers in size. But so is LSD and cocaine. They are also 1 to 2 nanometers in size. Drugs, vitamins, medicines that we're used to are nanoscale objects. Our body operates on the size of nanoscale. The ion pore complex, the ones that lets ions in and out of the cell, it's on the scale of tens of nanometers across. As a matter of fact, the actual image of it did not exist until 2 years ago, which I'll show you in a moment. The fact that our body is nanoscaled in size is maybe most powerfully shown in the DNA itself. How wide do you think the DNA is? One is always a good answer. It's 2, actually. It's 2 because it has a first molecule and a second molecule that are attached and perfectly matched. So it's about 2 nanometers wide. Now, the discovery of the DNA dates back, you can say, in 1860s. Someone suggested that if you look through the regular optical microscope at a human cell, there's some sort of goo inside the cell. What's that goo made of was really a fantastic question. And so people started asking questions, what's in that goo? And in the 1950s, Rosalind Franklin obtained that particular image. It's an odd image. It's a crystallographic diffraction image, X-ray diffraction image, that you shine X-rays, have very, very short wavelength onto of an object. If the object is periodic, there'll be interference of the bounced off light. And if that interference happens to be on the scale of the wavelength of the incident light, you'll get constructive and destructive interference. So by choosing the right X-rays that are very, very short in their distance, you'll be able to get a series of constructive and destructive interferences. That's what that pattern, it looks like X looks like. Except the odd thing is it looks like X. So it was suggested that maybe there is some sort of twisty periodic structure that maybe is inside the cells. And indeed, that led to Watson and Crick receiving the Nobel Prize for that work. Now, when they first suggested it, you think anyone believed them? Of course not. It's ridiculous. So what? Every one of our bodies has like a twisted molecule inside? That's ridiculous. It took a while, maybe a decade, for people to prove it and prove it over again. And they're like, oh, fine, we'll give you the Nobel Prize, fine. It is twisted. Now, that's, 1860s all the way beyond 1953. We're talking about 100 years, pretty much, of hundreds, if not thousands of people trying to ask a question of what's inside human cells. Versus today, you can go ahead and take a scanning tunneling microscope, put a strand of DNA under it, and take an image. And maybe you look at that image and you're like, I don't know if that's a twisted molecule. That's all right. I mean, that took you half a day. Do it a few more times. In 2 weeks, you'll probably tell me there's a twisted molecule that's inside every one of our cells. Yes, question.
Wait, so is like, why does it look like an X? Is it from the side because it's
It looks like an X because the diffraction happens to come from a twist itself. So the twisted geometry, I mean, you're talking about the 3 dimensions into a 2 dimensions, right? Because the X-ray image gives us a 2-dimensional image. But going from that's drawn as a 2-dimensional object, although we know it's 3-dimensional, to a 2-dimensional diffraction image, it's the periodicity.
Periodic this way, also periodic this way. Actually, see the period. See here.
And there's also periodicity this way.
That's why you see expansion of the periodicity.
I'll move on. 100 years or thereabouts of thousands of people reduced to a couple of weeks of one grad student. Why? Because we finally have the tools to see the nanoscale. We're just stepping into the age of nanoscale discovery. And images like this that were obtained 2 years ago at MIT Nano, facility just down the street here, call it down the block, would let you see images like this. Every one of the little nodules on this image is an atom. And this is a three-dimensional representation, as imaged, of the nuclear pore complex that is in a human cell. What was remarkable about this image is that it showed that the nuclear pore complex volume of it is about 75% larger than any previous image that was ever reconstructed. Why is that significant? It explained for the first time how HIV gets into human cells. HIV virus is too big to go through the nuclear pore complex if the size of the nuclear pore complex was previously as thought. Knowing now that it's 75% bigger, we actually have last year, the group of Thomas Schwartz captured the image of HIV going through the cell, through the nuclear pore complex itself, and hence explained how is it that the human cells get infected by these viruses. Nanoscale is amazing in many ways. Tools of today, remarkable, and can give us even these kinds of videos. This is of tungsten diselenide. Those are tungsten atoms that you can see dancing around, excited by the imaging process itself. As we are shining electrons to do the image, you have the bouncing atoms around, telling you about fissures and the opening of the cracks and the restructuring of the material, available to all of us to use and learn from. These tools, the ones I just shown you, are available for anyone to utilize on this campus and beyond. I just need to train you how to use the tools. And
Is there a sign up for that?
yeah, if you want to sign up, you can. It does cost $100 an hour or so to use it, right? Because there you go. In that case, you will find that we have hundreds of people across the world coming to MIT Nano to use MIT Nano as a tool set. And we've been around as a business available to the campus only for the last 5 years. So opportunities are vast because we can finally use these incredible tool sets to make discoveries like no one has seen before. There are many, many more things to show you. I know it's 1:30, I should stop. I will leave you with one unusual technology to consider. What if you can make a technology that is as, oops, how about that? That is as light as a feather and yet is as efficient as a silicon solar cell. If you can make a solar cell that happens to be 100 times, 120 times lighter than silicon, that can change the way you think about deployment of solar technology. That we can do. I'm holding one. And indeed can change the paradigm of what does it mean to deploy these cells over very large areas. Here is one of them connected to a motor, shine some light, and you get yourself a motion. Very light, very thin. What if, given the fact that many of you I'm looking around are very fashionably dressed, and you might find the color not necessarily matching, but very few of your shirts. What if I just give you this? I'll give you an invisible solar cell. One that happens to use nanoscale molecules, but chooses ones that are transparent to visible light, do absorb infrared light, and can generate electricity. That's generating 106 volts of open circuit voltage. But here is a video of one of them. Again, it's a transparent, invisible solar cell that if you attach a motor to it, make sure there is infrared light in your room, and you will be able to run an electronic device with it. There are many, many things that nanoscale enable us to do. If you're wearing glasses and you would like to power a Bluetooth radio with it, you can wear it and you can get tens of milliwatts of power from your glasses. If you would like to run your Kindle forever, just put it on top of a surface of a Kindle. Or if you want to replace 25% of the energy of a typical office building, just make sure all the windows happen to have a transparent solar cell on it. Because if we did, from when we started, installing so-called low-E glass windows, the ones that prevent infrared radiation from coming into your room, from warming up your room, if instead we had these infrared collecting solar cells on our windows, by now we would have been offsetting 2 gigatons of CO2 per year using these windows without taking any additional land. Yes?
How much does it cost to make like one piece, like maybe 1 square feet?
Are you talking about techno-economics again? How much does it cost? It actually, the cost of things depends on how much you're going to produce of something. If we could produce at the level of, gigawatts per year kind of factory, the answer would be it would be competitive with silicon. And silicon already is extremely, extremely cheap. Coming up with ways of, the hardest thing about solar technologies is not making a solar cell, is actually installing it. That's what costs most of the money. The solar, if I gave you a free solar cell today, 2/3 of the cost will still be kept. Free solar cell, but you want to install it, 2/3 of today's cost will still be kept. If I can make your installation simple because you happen to be installing the window anyhow, or because rather than having to wire the solar cells in a field, you'll use these light ones and just unroll a carpet and staple it to your roof, and that's your installation. If you can simplify the installation paradigms by rethinking the format of your solar cell, you can make it techno-economically much more valuable and much more deployable as a technology. Yeah, you have a plug that you go ahead and plug it in. Yeah, please.
What's the efficiency of these solar cells? Like how much of light do they per?
Yeah, it's a great question. I'm throwing away visible light. So don't expect me to be as efficient as silicon. If silicon can go on the window, then let's compete. But if silicon cannot go on the window, I win, even if I'm only 1% efficient, right? So the answer is that the way that to think of it is what's so-called Shockley quasar limit. Shockley quasar limit tells you when you absorb light from the sun, and the source is the sun, what fraction of the energy of that light can you convert in a form of electricity? For the best silicon or such solar cells, it's about 30% because of all of the thermalization and so forth. These 20%, because I'm throwing away some of the light that I cannot get, that, because otherwise they would not be transparent. Yeah. And if I'm on a different solar system, it'd be a different number, right? Because it depends on the color of your sun. Yeah.
We have some online questions. The first one is nanotechnology research viable for undergrads? And how do you recommend students get into this field?
Absolutely, it's viable for undergrads. You guys use nanotechnology every day. So why would it not be viable for you to step into? The way to explore these is recognizing your hands can do many more things than simply type on a keyboard, right? Which we are really good at, all of us. But we have sometimes stop right there because we feel like, well, maybe the access to the lab is not as easy. If you're an undergrad at MIT, for example, you can step into MIT Nano, and actually, we would give you money to step into MIT Nano. We actually will give money to your advisor so that they can sponsor you as you do a project with them. There has to be intellectual reason for stepping into the space. And at MIT, roughly speaking, 2/3 of all of our engineering faculty use nanoscale to make their discoveries. And about half of all of our science faculty use nanoscale to make their discoveries. So if you're a part of the 2/3 of the research groups of engineering or 1/2 of the School of Science, you have a project that is nanoscale related. And so stepping into MIT Nano would be a natural thing to do.
Thank you so much. Another question is, how can startups in this field or in general know if their idea is techno-economically viable?
You never know if your idea is perfectly techno-economically viable, but you can always go through the numbers. We do teach classes on techno-economics. Roughly a quarter of all of the undergrads of MIT will at some point end up in a startup or launch a startup. So teaching you how to launch a startup, techno-economics of it, and how to pitch a good idea is almost as important as teaching you physics, just from perspective of where your next job will be. And so exploring those parameters, we spend a lot of time asking question of how can we assist you? So in an ecosystem like Boston, there are many, many ways to assist you in the process. Universities are a fantastic place to start.
Yeah, we're over time a little bit, so we can move to our t-shirt presenters. If we could get Michelle and Noah on the board, that would be great, from microelectronics.
All right. Hi, my name is Michelle Che. I'm from the microelectronics course. I really appreciated your presentation, and I think you gave us a great understanding of how long we can expect to get new developments. And I also thought it was really interesting how even people in like the Middle Ages were using nanotechnology with things like metals and gold and silver.
Hello, my name is Noah Lee, and I'm also from the microelectronics core. Thank you so much for your talk today about nanoscale and how pretty much encompassing it is in our whole world. I especially found it exciting and about how you highlighted the manipulation of wavelengths with Q dots to create really, really pure colors and the importance of like accuracy imaging. It's really cool. So we'd like to present you with a shirt from BWSI.
Fantastic. Oh my gosh. Thank you. Thank you.
Thank you so much.
Thank you. Thank you.
Why don't we just take a picture looking this way?
Of course.
So if you stand here,
I should stand right here.
everybody moves over. Right.
Okay.
Brad, here. Right here.
Okay.
You can take it from here.
But everybody behind me.
This is great.
You could even take a selfie.
I was going to say, if I can take a selfie, that'd be awesome.
Yes. Still young and hot.
Yeah, there we go. Please, please. Please, I have most of us. Here we go. All right, everyone smile. There we go. Woo. Can you guys like raise your hand or something, or?
BWSI is.
Thank you.
Hold on, we're gonna take a show. Hold on, hold on. It's